In the previous video, we saw some basics of probability where I discussed the union bound and some basic tail bounds, which were Markov's inequality, Chebyshev inequality, and the Chernoff bounds. In this video, we'll explore sequences of random variables. How do we classify different kinds of random variables? How do we classify different sequences of random variables depending on their joint distribution, and what properties do these have? So sequence of random variables, so typically in this course, uppercase letters, capital letters will denote random variables, whereas small letters or lowercase letters will denote realizations of those random variables, and vectors, random vectors or sequences of random variables will be denoted with a superscript. So xn denotes the sequence x1, x2, x3 up to xn, right? So we say that a sequence of random variables x1, x2, x3 up to xn is independent and identically distributed. So independent and identically distributed will be abbreviated to IID. If all of these xi's are, if they're jointly independent and they all follow the same distribution, say px. So this is IID with distribution px if the following happens. So we'll give a formal definition of what it means for a sequence to be IID, and basically what it means is that the joint distribution factorizes into the product of the marginal. So x1, x2, x3 up to xn. So the joint distribution of all of these random variables is equal to the product. So they're all independent. So this is equal to the product I going from 1 through n of pxi of xi, but then they're also identically distributed. So this is the product I going from 1 through n of px1 of xi. So we assume that the distribution is px, so it's px of xi, right? So for example, if we have two IID random bits, or three, so let's say that x1, x2, x3 is IID Bernoulli 1/3, then px1, x2, x3 of, let's say, 0, 1, 0 is equal to px of 0, px of 1 times px of 0, which is 2 by 3 times 1 by 3 times 2 by 3. Okay, so all of this is straightforward. So now we know what it means for a sequence of random variables to be independent and identically distributed. Now, a very important result for IID sequences of random variables is the so-called weak law of large numbers, and this is captured by this very simple example, which is the following. If you take a single coin and you keep flipping it, if it's a fair coin, you keep flipping it, then the average number of heads or average fraction of heads is roughly equal to a half. And this is formalized by the weak law of large numbers. So it's the weak law of numbers, which says that if x1, x2 and so on are independent and identically distributed, and according to some distribution px, and the mean expectation of, let's say, x1 equal to mu. So if it has finite mean, then the average converges to the mean. And how does it converge? It converges in the following sense. So the probability that the empirical average 1 over n summation I going from 1 through n xi, so the absolute value of the empirical average and the true mean tends to 0 as n tends to infinity. So for every epsilon greater than 0, the probability that this is greater than or equal to epsilon is 0. So the limit as n tends to infinity, this probability tends to 0. Okay, and so this is the weak law of large numbers. And how do we prove the weak law of large numbers? I won't prove this, but here's a hint. Use some of the inequalities that we saw in the previous lecture to prove this result. To prove that, you can use the assumption that the variance is also finite. It's finite, but doesn't matter what exactly it is, right? Okay. Now, we've seen what it means for a sequence of random variables to be independent and identically distributed, and this is the case where there is absolutely no memory in some sense. So x2 contains no information about x1, x3 contains no information about x2, and so on. So there is really no dependency among the random variables. Now, if you look at, say, English text, there is a lot of dependency among the characters, right? Or the words. So if you just pick up words independently and identically from the dictionary, then what you get is a string of gibberish. It doesn't resemble English language anymore. So what we do is to model strings such as valid English text, we introduce some kind of a dependency. Okay, and the simplest form of dependency is in the form of a Markov chain. So we say that x1, x2, x3, so on form a first order Markov chain if the following happens. So it's a first order Markov chain if given xi, so in the simplest case, so given xi, xi minus 1, so on up to x1. So for any j greater than I, pxj given x1, xi minus 1 all the way up to x1 is the same as pxj given xi. So given xi, everything in the future, that is xi plus 1, xi plus 2, xi plus 3 and so on, all of them are independent of the past. So if you want to know something, then you just look at one step in the past. So xi plus 1 depends on xi, but given xi plus 1 is independent of everything else in the past. Now this does not mean that xi is unconditionally, it does not mean that xi plus 1 is unconditionally independent of x1, conditioned on xi. So given that the value of xi is something, everything in the future is independent of everything in the past. Okay. Sorry. Yeah, so one example of a very simple example of a Markov chain is the following. So let us suppose that you're successively tossing coins, and you count the total number of heads that you have seen up till now. So those coins, and xi is the number of heads you see in the first I tosses. Right? So initially you toss a coin, maybe you get a head, so x1 is 1. x1 is 1, and then you toss it again, maybe you get a tail, so it's still 1. You toss it again, maybe you get a tail, it's still 1. You toss again, maybe you get a head, it becomes 2, and then you toss it again, maybe another head, 2, and so on. So now note that, so if this is x1, x2, x3, x4, x5, and so on, x2 and x3 are not independent of each other. So x3 can at most be 1 larger than x2, but it can't anyway be smaller than x2. Right? It can be equal to or 1 larger than x2. So they're not independent of each other, but given x2, x3 is independent of x1. So it doesn't matter what x1 is, but if x2 is 1, then the distribution of x3 does not depend on the distribution of x1. So in particular, I want you to pause the video and tell me what the distribution of xi is, or x2, sorry, what the distribution of x3 is given x2. Right, so pause the video and think about it. Okay, so note that if x2 is equal to b, then x3 can be, at most, can either be equal to b or b plus 1. It can't be anything else, right? So the probability of seeing a, of that x3 equal to a given x2 equal to b, is 0 if a is less than b or a is greater than b plus 1. So we can immediately rule that, right? So if a equal to b, then it means that we saw a tail, right? And so this is simply the probability of seeing a tail, right? So the only other case that is left out is a equal to b plus 1, and this is equal to the probability of seeing a head, right? So this is the conditional distribution of x3 given x2, and this certainly forms a Markov chain. All right. So this, note that the distribution of the distribution px3 given x2 really is different from the distribution of px2 given x1. So px3 given x2 is not the same as px2 given x1, because because the maximum value that x3 can take is what? The maximum value that x3 can take is 3, but the maximum value that x2 can take is only 2. So this is indeed a valid Markov chain, but it is not what is called time homogeneous. So px3 given x2 is not the same as px2 given x1. So we'll define a Markov chain is time homogeneous. So this is a sequence of random variables is a time homogeneous Markov chain if of course the xi's form a Markov chain is a valid Markov chain and pxi given xi minus 1 does not really depend on I, so it is the same as px2 given x1 for all I. Okay, so this is the definition of a time homogeneous Markov chain, and to completely specify a time homogeneous Markov chain, you need to specify two things. One, this conditional distribution, which is sometimes called the kernel of the Markov chain, or the transition probability of the Markov chain. So the transition probability is px2 given x1 and the initial distribution, which is px1. So once you specify these, the joint distribution becomes automatically specified. So for a time homogeneous Markov chain, px1, x2, x3 up to xn of little x1, little x2 all the way up to little xn can be factorized as px1 of x1 times the product I going from 2 to n of p xi or given xi minus 1 of little xi given xi minus 1. So this is px1 of x1. Since this is time homogeneous, this is I going from 2 to n of px2 given x1 of xi given xi minus 1. Okay, so let's see an example of a time homogeneous, first order time homogeneous Markov chain. So this is first order. So every random variable depends just on depends on something which is one step in the past. So conditioned on one step in the past, it's independent of the remaining history. So one such example is something similar. So let's consider the following random process where everything is Bernoulli. So xi is, so x1 is generated as a Bernoulli half random variable, okay, and x2 is equal to x1 plus an independent Bernoulli 1/3 random variable. Okay, so you first generate a Bernoulli random variable, so toss a coin, toss a fair coin. If it's a head, then it's a 1. If it's a tail, it's a 0. Now to this x1, you add another Bernoulli random variable, so you toss a coin again, you get either a 0 or a 1. But this coin is not fair, it's 1/3, so probability is 1/3. So if it's a 1, then you add a 1, you XOR a 1 with the previous one. So here by sum I mean the XOR, sorry. So each xi, so x3 is x2 XORed with a Bernoulli 1/3 random variable and so on, right? So each of these is an IID Bernoulli random variable. Okay, so in other words, so one way of looking at this is the following. So you first generate a Bernoulli random variable x1, and then you generate Bernoulli random variables y2, y3 and so on. So x1 is Bernoulli half, and y2, y3 and so on are IID Bernoulli 1/3. Okay, and x2 is x1 XORed with y2, x3 is x1 XORed with x2 XORed with y3, x4 is x3 XORed with y4 and so on, right? So in effect x3 is x1 XOR y2 XOR y3, x4 is x1 XOR with y2 XOR with y3 XOR with y4 and so on. So now note that conditioned on x3, x4 is independent of x2 because x4 is generated by adding a Bernoulli 1/3 random variable to x3, right? So indeed you should verify this yourself by actually computing the probabilities. So verify that p x1 x2 x3 of, let's say, 0 1 0 or 0 0 0 or 0 0 1 is the same as px1 of 0 times p x2 given x1 of 1 given 0 times px3 given x2 of 0 given 1. Right? And the same holds for all possible combinations of x1, x2 and x3. Okay, so that's what it means for something to be a time homogeneous Markov chain. Now this is a first order Markov chain where the dependence is only on one step in the past. Similarly, we can extend this to general kth order Markov chains. So we say that x1, x2, x3 and so on, a sequence of random variables, is a kth order Markov chain if the following happens. So p xi given xi minus 1, xi minus 2 and so on all the way up to x1. So this is the conditional distribution of xi given xi minus 1, xi minus 2 all the way up to x1 is the same as pxi given only k steps in the past. So xi minus 1, xi minus 2 up to xi minus k. And a consequence of this is that for all j greater than I greater than k, p xj given xi minus 1, xi minus 2 all the way up to x1 is the same as pxj given xi minus 1 up to xi minus k. So when k is equal to 1, you get a first order Markov chain. What happens when k equal to 0? Think about that. So the larger the k, the more dependency you have, because each xi depends on k steps in the past. But if k is small, then the dependency is less. So the larger the k, the more dependency you have, and by varying k, you can get different Markov chain distributions. But typically, at least in this course, we'll be interested in independent and identically distributed sequences, although along the way I'll be mentioning some results without any proofs for general first order or kth order Markov chains. So one thing to note is that practically, when we're talking about English text, we do model this as a kth order Markov chain for k to be sufficiently large. There are more complicated random processes, more sort of random models which capture English text and different kinds of problems, but typically the ideas that you develop for independent and identically distributed sequences can be modified in some sense to hold good for Markov chains as well. So at least in a first course in information theory, which is this course, and in source coding and channel coding, we'll generally study independent and identically distributed sequences, but a lot of these results can be generalized to first order and more general kth order Markov chains as well.